I will start. I'm starting the recording now for our, so that I will make this second lecture available on Moodle as well. So good afternoon, everybody. Welcome to our second class of our Inorganic Chemistry course. So today we will continue our discussion on atomic properties and periodic trends that we started in the first lecture. And the idea is to finish this discussion today and then start covering acids and bases, which is the next topic of our course. All right, so previously, like in our first lecture, I told you guys that inorganic chemistry in this course, we will take a journey throughout the periodic table, studying various aspects of the elements, various properties, and how these properties also vary across the periodic table, and how the periodic table can work for us as a way to systematize and understand how these various properties vary for the elements as a function of their atomic number. So in the first lecture, we discussed some periodic trends, and then we covered atomic properties or several atomic properties, such as the size in the framework of the atomic radii and the ionic radii. We covered ionization energy, electron affinity, electronegativity, and then we finished our discussion by talking about polarizability and occurrence of the elements. And for all these kind of properties, we discussed how they vary across the periodic table. So we have seen that the periodic table, therefore, provides an organizing principle for the elements, in which the definition of periodicity is the regular manner in which physical and chemical properties of the elements vary as a function of the atomic number. And just by looking at the position of each element in the periodic table, we can already know what is their valence electron configuration. So as we saw, this is the general organization and labels for the elements in different places in the periodic table, which we covered in the last lecture. And these were the main atomic properties that we covered, and the results can be systematically summarized across the periodic table, as we can see here in this figure. And then in the homework, I asked you guys to do a similar type of exercise as well. And then I recommend that you guys do that thinking, not just checking on this slide directly, because you know this slide is already kind of like, it will give you the response for you. So here we can see, for example, the variation on the atomic radius. So it increases on these directions from top to bottom and from right to left in the periodic table. Same here, tendencies for electron affinity, tendencies for electronegativity, trends for ionization energy. And also here in the table is described metallic character and trends in metallic character for the elements, which we did not see. We did not cover this in our first lecture, but this is exactly the point in which we will start. So this will be the first topic that we will cover here today. So the idea for today is to finish our discussion on atomic properties, talking about metallic character and oxidation states for the elements. Then we will cover properties of compounds, and then like some properties or compounds made up of the elements on the periodic variation on the properties of these compounds. And more specifically, regarding the properties of these compounds, we will focus on coordination numbers, bond enthalpy trends, and we will discuss like some binary compounds as well, such as oxides, for example. And then we will finish this discussion of this first topic of our course, which is periodicity and atomic properties, by describing the anomalous nature of the first member of each group, as well as diagonal relationships, which are pretty important in the periodic table. Okay, so let's start by talking about metallic character. So when we talk about a metal, we can infer that their chemical properties of these metallic elements can be considered like they arise from the ability of these elements to give up an electron and produce metallic bonding. So in a metal, we have like the elements of the same composition, for example, gold, several atoms of gold bond together. So for this bonding to take place, all these atoms have to form chemical bonds among themselves, and this becomes easier when they give up an electron to produce metallic bonding. Therefore, if this arises from the ability of the elements to give up an electron and produce the metallic bonding, therefore, this means that elements that have low ionization energies, because the ionization energy is the energy required to remove the outermost electron bound to an atom. So if an element has a low ionization energy, this means that it will have a good ability to give up an electron to produce metallic bonding. Therefore, elements with a low ionization energy are likely to be metals, and those, therefore, as a consequence, with a high ionization energy are likely to be non-metals. Therefore, the metallic character of the elements varies according, like in agreement with the trends in ionization energy. So the metallic character decreases across a period, decreases when we go right to left in the period, and increases as we go down a group. So actually it is like this, the trend. Decreases across the period, so increases from right to left, and increases down a group. So these trends are related to the trends in atomic radii. So the larger the atom, the lower the ionization energy. So these are related. And then therefore, atomic radii or size, as well as ionization energy and metallic character are all related to each other. So here we have a periodic table showing the variation in metallic character across the periodic table. So we see a decrease in the metallic character as we go across the period or from left to right, and an increase in the metallic character as we go down a group. And here we have the elements classified as metals, non-metals, or metalloids in the periodic table, showing that we have this kind of trend that the metallic character increases in this direction. All right, now we can take a look at the trends in stable oxidation states for the elements. So these trends in stable oxidation states that each element can have, this correlates well with the position that this element is in the periodic table by considering their electron configuration. So there is a correlation between the stable oxidation state and the electron configuration of this atom, which can be inferred from the position of these species in the periodic table. There are some related factors, such as the ionization energy and spin correlation, that also play a role. So in terms of spin correlation, it can be stated that elements having a complete or a half full or a half full valence shell, this has a greater stability than a partially filled shell or partially filled electron configuration. Therefore, the atoms will have a tendency to gain or lose electrons until they acquire that configuration, complete or half full valence shell. So for example, when we talk about the main group elements here, referring to elements in the S and the P blocks, the group oxidation number can be predicted from the electron configuration of the element. So for example, in group 1, 2, and 13, so here we have main group, the oxidation states or the stable oxidation states will be +1, +2, and +3 respectively. Therefore, they will have the tendency to lose electrons to make their inner to achieve complete shell configuration. And this can be achieved, therefore, with a relatively small input of energy. So that's why these are the stable oxidation states for these elements. So when we go like from groups 14 to 17, so talking about elements at the head of group 14 to 17, or on the top of groups 14 to 17, it becomes more energetically favorable for these atoms to accept electrons in order to complete their valence shell. So if we talk about group 14, 15, 16, and 17, they therefore have oxidation numbers -4, -3, -2, and -1 respectively when they are combined with less electronegative elements. For the group 18, actually, these are the noble gases in which the elements already have a complete shell or a complete octet of electrons, and therefore they are neither readily oxidized or reduced. So their oxidation states are zero. Okay, so these trends here that I mentioned for group 14 and 17 were for the elements on the top of the group, but then when we go for the heavier elements or elements down the group in the P block, actually there is an interesting behavior that arises. Actually, the heavier elements of the P block can also form compounds in which the element has an oxidation state or an oxidation number which is 2 less than the group oxidation number. So for example, for group 13, the group oxidation number would be 3+. Therefore, heavier elements can also form compounds with the oxidation state 1+, or oxidation state which is 2 numbers less than the group oxidation number. And this relative stability of this oxidation state in which the oxidation number is 2 units less than the group oxidation number is an example of the inert pair effect. So in this case, for group 13 that I just mentioned, while the group oxidation number is +3, the +1 oxidation state increases in stability when we move down the group. And this inert pair effect is often assigned to the large energy that becomes needed to remove the remaining ns2 electrons after the np1 electron has been removed. So this happens for the heavier elements of the p block, and this is the inert pair effect. All right, for the now going to the D and F block, so moving away from the main group, here the group oxidation number is achieved in the D block only for groups 3 until 8. And even then, like, we need highly oxidizing species to achieve the group oxidation number. And these highly oxidizing species are, for example, fluorine and oxygen. So oxygen can bring the group oxidation states for many elements of this part of the D block, like from group 3 to 8, much more easily than fluorine, because fewer oxygen atoms are needed to achieve, like in a compound, to achieve to raise this oxidation number, as oxygen has oxidation number of 2 minus, while fluorine is 1 minus. So we need less oxygen atoms around the metal of the D block to achieve the group oxidation number. So this reduces the steric crowding. So that's why oxygen is more effective in this way. So here we have, like, for the 3D series of the elements of the first period of the D block, here we have the different elements. So here's group 3, 4, 5, 6, group 7, 8, 9, 10, 11, and 12. Here we have the electron configurations, and here we have all the possible oxidation states that are observed for these elements. So we can see that the group oxidation state until here, group 7, sometimes in group 8 can be observed. But for the elements on the right of manganese, for example, is very rare. And here also you can observe one of the key properties of the transition metals, which make their properties so interesting and so different and unique relative to the main group of the elements. So the main, like, unique feature of these transition metals or transition elements that give to many interesting properties is the fact that they can possess a variety of different oxidation numbers. So this is a very interesting fact, and you will see this even more when we discuss coordination compounds in the last part of the course. But this plays a central role towards catalytic properties, which involve redox processes and the metals changing oxidation state in different stages of a catalytic cycle, for example, and also in terms of other properties such as optical properties and magnetic properties as well. So this is what makes transition metals so unique and interesting. All right, so up to manganese that we saw, like, the group oxidation state can be achieved, which therefore indicates that all the 3D and 4s electrons can participate in the bonding. And therefore, we can have that the maximum oxidation state corresponds to the group number. As we saw here, here we have the maximum oxidation states corresponding to the group numbers. Okay, so after we exceed the 5D electron configuration, what happens is this tendency for the d electrons to participate in the bonding decreases, because in this case, we have an increase in the effective nuclear charge for the elements. And therefore, this means that the high oxidation states are not observed and become less and less favorable, as we can see here as well, in which the higher oxidation states become less and less possible to be achieved. And these trends in the various oxidation numbers for the transition metals can also be visualized by this type of diagram, or this type of diagram representation, which shows oxidation number here in the x-axis, and on Y we have energy. So this means that species that are lower in the diagram are more stable. So we can see that the group oxidation states for scandium, titanium, and vanadium fall in the lower part of the diagram, right? So they are below zero, which means they are negative, therefore they are stable. So the group oxidation numbers here, for example, for scandium is +3, for titanium is 4, and for vanadium is +5. So this group oxidation number is below zero, so they are negative. Here is the zero part. Therefore, this means that these elements can be oxidized to achieve the group oxidation numbers. So here are the group oxidation numbers. Species in the group oxidation state for chromium and manganese, which is therefore for chromium +6 and manganese +7, they are in the upper part of the diagram. They have positive values, which means that, you know, they have a lower stability, as we may say, which indicates that they are very susceptible to reduction, because if they acquire lower oxidation states, they become more stable, their energy becomes more negative. So these species, therefore, species in the group oxidation state for chromium and manganese, therefore, they are very susceptible to reduction, which means that they are very strong oxidizing agents. And then we will see this also when we cover oxidation and reduction, which will be the next topic after acids and bases. So when we talk about groups 8 to 12, so iron, cobalt, nickel, copper, and zinc, we can see that the group oxidation state cannot be achieved. So if we take a look at iron here, we see until oxidation state 6, cobalt until oxidation state 4, nickel until oxidation state 2, copper also 2, and zinc here also 2. So this diagram shows also the oxidation states that are most stable under acidic conditions, right? Because we can guess because this diagram was constructed by acidic condition, and from this diagram we were discussing like the group oxidation numbers, their relative stability, tendency to be reduced or not. But it also can show us and tell us what are the most stable oxidation states for these elements, which is the first period of the transition metals, or the 3D series. And therefore, by looking at these diagrams directly, we can know which are the most stable oxidation states under acidic conditions. So what are they? So for scandium, which is the most stable oxidation state under acidic condition? Yes? Somebody? This is easy because there is only one here, right? So it's +3 for titanium. Yeah, thank you, Adam, for titanium. So titanium, we have these species here, and also 0. Which one is the more stable oxidation state? 3+, it's right. 3+. So even though titanium is in group 4, the most stable oxidation state is 3+ in this case. All right, vanadium. It looks like it might be 3+ as well, right? 3+ as well. So here we have, for chromium, this is the idea. Just check which one has a more negative energy. Manganese. Manganese will be +2, and so on. Okay, iron, +2, if we take a look at the curve for iron. For cobalt, also +2. Nickel, +2 as well. In copper, what's the most stable? +1, but actually that was a good one because the +1 is it's here, right? Because we are comparing +1 and +2, but actually it's right that it's 0 because 0 for all the elements is here. So for copper, 0 is lower than +1 and +2. So in this case, is actually 0. Okay, good. All right. So this is like, yeah, elemental copper, exactly. In this case, copper, 0. Yeah, so this with this we can shift then our discussion now to coordination number. So what is the, does anybody know what is the definition of coordination number? The coordination number can be defined as the number of intermediate neighbors or intermediate atoms that a central atom possesses when it's part of a compound, right? So like if we have a metal, for example, binding to 4 different species, this means coordination number of 4. If it's surrounded by 6 other atoms, then the coordination number is 6. So it's the number of intermediate atoms surrounding the central atom when it's part of a compound. So the coordination number of an atom in a compound depend very much on the relative size of the central atom and the size of the surrounding atoms, because here the sizes will determine how many atoms can fit around the central atoms. And this is dependent on the size both of the central atom and the size of the surrounding atoms as well. So when we are talking about the P block, we have that low coordination numbers are most common for compounds of the period 2. And higher coordination numbers are then observed when we go down a group, because this means that the radius of the central atom increases. So if the radius of the central atom increases, this means that we can fit more atoms around the central atom. So one example, for example, nitrogen can form 3 coordinate molecules, or molecules with coordination number equal 3, such as the 3 nitrogen 3 chloride, and also 4 coordinated ions, such as ammonia. Phosphorus can form molecules with coordination numbers 3 and 5, as shown by the chlorides, and also 6 coordinate species, such as this chloride, for example. So we go down the group in this case, and then we can see that higher oxidation, higher coordination numbers can therefore be achieved. All right, but when we go to the D block, so we have a similar trend when we go down a group. So the elements in the 4D and the 5D series, they tend to exhibit higher coordination numbers than the elements of the 3D series. So when we go down in the D block, elements tend to have higher coordination numbers, and this is also occur because of their larger size, right? And then also remember that the elements of the 5D series have similar sizes relative to the 4D series as a result of the lanthanoid contraction that we covered in the first lecture. So when we have compounds with fluorine, or in which fluorine acts as a ligand, and these nomenclatures of ligands and central atom and these things we will also cover in more detail in the third part of this course when we talk about coordination compounds. So when we have this small fluorine ligand as the species forming these compounds with elements of the transition series. So with 3D series metals, fluorine tends to form 6 coordinate complexes. And for larger metals in the 4D and 5D series, in the same oxidation state, we can have like even higher coordination numbers, including coordination numbers 6, 7, 8, and 9. So because of their larger radii, we can have, therefore, higher coordination numbers. Okay, so I believe the last type of periodic trend that we will discuss for the elements is the bond enthalpy trends, or the energies of the bonds formed by these elements when it's part of a compound. So let's assume a generic element here, or a generic atom called E, and then there are 2 scenarios when this element does not have lone pairs and when the atom has lone pairs. So without any lone pairs in the atom that we are analyzing when it's forming the compound, so when it forms a bond with another element, so a EX bond here. So for an atom, if the atom does not have any lone pairs, it means that the bond enthalpy decreases down a group. So the bond energy, or the bond enthalpy, becomes lower or decreases when we go down a group. And this is because when we go down the group, size increases, so these bonds tend to become longer in length because the atoms are farther away from each other, or the core, the nucleus of the atoms become farther away from each other. So the bond longer, bigger, bonds that are bigger in size tend to be weaker. However, when we have an atom that has lone pairs, so if E has a lone pair of electrons, then this bond enthalpy typically increases between periods 2 and 3, and after that, it decreases down a group. And then we will try to understand why this happens. All right, so the mean EX bond enthalpies for atoms that have lone pairs typically decrease, like overall, like the overall trend is that it decreases as we go down a group in the P block, and this is because the elements become larger as we go down a group. So there's an increase in size as we go down the group. However, the bond enthalpy for the element at the head of the group, or the first element of the group, is anomalous and smaller than that of the period 3. So this is why it increases from period 2 to period 3, and then after period 3, it also decreases. In other words, for the first group, for the first element of the group, there is an exception when there is lone pairs, which makes these bond enthalpies much smaller than for period 3. And then we can see this trend here for nitrogen and phosphorus, for example. So these relatively weakness of this bond, or what makes this bond energy smaller than what would be expected of for the atoms or for the elements of the top of the group, or the first element of the group, is because these atoms are smaller, so they are closer together, right? So this would give rise to a stronger bond, and therefore a higher bond enthalpy. However, because they have lone pairs, right, in this case, what happens is as they are very close together, also the lone pairs on the neighboring atoms also become very close together. And as a result, they repel each other. So we have electron pair repulsion between the neighboring atoms. And this is very significant. And this electron pair repulsion in the neighboring atoms make, therefore, the bond enthalpy weaker. So that's why we observe this. So because of the proximity of the lone pairs, which leads to repulsion between them, so this weakens the bond. And this is observed here for the bond of two nitrogen atoms, but we can also observe this when we have nitrogen with another type of element, such as chlorine, for example. You can see these trends also occurring. So when we have an element now that has no lone pairs, then we don't have this kind of anomalous behavior for the first element of the group. Then in this case, the bond enthalpy usually decreases as we go down the group. So we can see here for group 14, carbon and silicium, for example, we can have, we can see and carbon is the first element of the group, and we can see this trend, therefore, that the bond enthalpies decreases down the group. And then, therefore, the reason, as we already discussed, is that smaller atoms can form stronger bonds because they're closer, they can be closer together. Therefore, the shared electrons become closer to each other and closer to each of the atomic nuclei. And in these cases specifically, we can observe here that for the silicium chlorine bond, this bond is particularly strong, or it has a strong bond enthalpy, and this occurs by the fact that in these two kind of when these two kind of elements combine, the atomic orbitals of these two elements have very similar energies, and therefore this leads to a very efficient overlap that leads to very strong bonding, which therefore leads to this increase in bond enthalpy that is observed here. Okay, so when we go to the D block now, so we were talking about the P block, and now we are going to talk about the D block. So in the D block, the trends in bond enthalpy are a little different. So in the D block, the bond enthalpies generally increase down a group. So instead of decreasing, now in the D block, bond enthalpies increase down a group, which is the opposite to what we just discussed for the P block. And this is because in the D block, we have the D orbitals. And the D orbitals are very unique because they become more effective at forming bonds as we go down the group and as they expand in size. So as we go down a group, the D orbitals or in the elements expand in size, and the D orbitals, they move from being too contracted to being more bigger or more expanded, and this creates a better bonding, and this better bonding or better conditions for efficient overlap with other orbitals such as 1s, 2s, and 2p orbitals of other elements when forming a compound. So that's why we observe this increase as we go down the group. Okay. An exercise before we go to our break. Explain why elemental sulfur forms rings or chains with sulfur-sulfur single bonds, while oxygen exists as diatomic molecules. So oxygen does not form rings or chains with sulfur-sulfur single bonds. All right, so I'll give you guys 3 minutes to think about this. 3 minutes to think about this. You can guys try to discuss with each other if you want, and then let's see who can give me a hypothesis for this or an explanation for this first. But in this case, please don't Google. Let's try to think. So I will help you actually, because what we have to do is try to think about the bond enthalpies for sulfur and for oxygen when they are forming compounds with each other. So think about the bond enthalpies for a sulfur-sulfur bond and for an oxygen-oxygen bond. And think about what would be probably the difference between the enthalpies for a single sulfur-sulfur bond and a double sulfur-sulfur bond and a single oxygen-oxygen bond and a double oxygen-oxygen bond. So this is the key, like looking at these different bond enthalpies. Okay, so as I was mentioning, we need to consider the relative magnitude of these bond enthalpies for the single and double bonds for oxygen and sulfur, right? All right, so if we look at the single bond, so this has like lone pairs, so we can see that for the single bond, the sulfur has a stronger, higher bond enthalpy. So stronger bonds are formed here for the single bond here for sulfur. And then when we compare a single bond with a double bond, right? The single bond will always be weaker than the double bond. So the double bond is always stronger relative to a single bond. So this occurs both for sulfur and for oxygen if we compare the single and the double bonds. But the key here is that for oxygen, the double bond is much stronger. So it's more than 3 times as strong as the single bond. And therefore, there is this stronger tendency for the oxygen to form the double bonds relative to the single bond in this case. For the sulfur, even though the double bond also has a higher energy relative to the single bond, this double bond is less than twice as strong as the single bond. So this tendency to form this double bond is not as strong as in the case of the oxygen. And in this case, of course, the way that these compounds appear or the way that these compounds exist also depends on a variety of factors. But in this case, because these differences are not so high, the single bonds are more favored. So let me check here what you guys are writing. Interesting things in the chat. Yes, makes sense. The double bond is stronger than the single bond, and for it's a bond is stronger. Yes, yeah. So this is right to explain why the double bonds are better than, like, are stronger than the single bonds. Okay, so with this, we finished this discussion of various atomic properties actually, and the variations across the periodic table, and we will start discussing binary compounds. So before we start this discussion, then I recommend that we take a 10 minutes break, if that's okay with everybody, so we can get back to this at 1:17 p.m. Is that okay, everybody?